So good morning, everybody. Welcome to the first day of Greenbuild Expo. Hope everybody's excited as I am. My name is Ian Malloy. I'm a Senior Product Manager at Autodesk. I work with the Generative Design and Building Performance Analysis groups, which is part of the AEC division. I'm sure you're all in the right class by now. You've seen the title sitting there for a while, and I'm sure you read the description and the learning objectives so that you know roughly what we're going to be talking about here. Just, in summary, we've got some really exciting new things to share with you. Really think that makes energy analysis a lot more efficient, particularly for architects. So I just wanted a quick question, just out of curiosity, how many people in the audience would call themselves architects? Okay, so about half. And what about engineers? So we let a few in. Okay, that's okay. You're all right. So the first thing I wanted to start with was just to explain why I titled this Agile Energy Analysis for Architects. At Greenbuild, these classes are always interesting to learn from other industries. And something that we've noticed at Autodesk, being a software and technology company, is that building better software has actually got a lot in common with building better buildings. And Agile, or the Agile movement, is something that has really transformed the software industry in the last decade or two, and it wouldn't be right to sort of start and introduce this to you. Just out of curiosity, how many people have heard of this before, Agile software development? Okay, a handful, okay, so. But I think about in 2001, a group of software developers got together and said, there has to sort of be a better way of developing software. And this website, it's a very simple and unassuming website. If you just read some of the text yourself there, you'll kind of see roughly what it's describing. But some of the things that are nice about it is that it's talking about, we know there's a better way to build software. The things that we prioritize are how really teams interact and how teams work together, and how we prioritize, working software over, really good documentation, and also working very closely with the customer to understand what their needs really are, so that we end up with a better product. And of course, responding to change. Now, of course, just like the building industry, the software industry is ginormous, and it can't be summarized in this sort of one simple slide. But it really is kind of like the very sort of starting introduction point to this whole. Domain, which has really spawned a whole range of different methodologies and so on, and they share a lot of commonality, but at different levels of detail. So you'll have heard of things like Scrum, XP, and then more exotic names like Kanban, Scrumban, and so on. I don't want to get into the details. Some of you may have heard of like the Lean Startup. Have you ever read that book? So these are just some of the things I would just to point out that what they really talk about is a very different approach to designing and building really anything. It's not just software. It can be applied. It came out of the software industry, but of course it borrowed from other industries as well. And originally the software industry actually borrowed from the construction industry in terms of what was called a waterfall process. You design, then you build, and so on. But the point is, there's a large domain of knowledge in this area around how software is built, and it's all about really building a better product. The end product and the value that it's created is better. So I just wanted to start off with just describing that, and just to sort of reflect on how we as a software company look at this problem, how we've used these methods to learn, and how they've actually produced a tool that I'm going to share with you here today to kind of help you do your jobs. So Agile is normally positioned against its sort of opposite, which is called Waterfall, and really the two methods just lie at a kind of a different end of a spectrum from predictive to adaptive methodologies. And what you'll see on Waterfall, there's a very deliberate set of steps that one feeds the next, whereas with adaptive and Agile, it's much more iterative, shorter cycles where you're constantly designing, building, and testing, as you go. So the idea is things on the left are sort of plan-driven. You treat the system as a series of parts. There's a series of handoffs, and you test at the end. Whereas with Agile, that's all done together. You're looking at the system as a whole. The team is integrated, and you're sort of testing continuously. Now, this isn't to say one is right and one is wrong. It's just that they're suited for different purposes. But the reality is most software today that you see, probably about 80% of it are using these Agile methods. Some software projects like, military type things, or, banking, and certain things that have very particular requirements that can be very clearly understood, still suit a waterfall development. So it's not that either of these are wrong. Remember, it's a spectrum. to give you another sort of perspective on this, what do we mean by this? And this is people have an inherent sense of this, particularly being designers, you understand what these things are. But again, I think it's sort of sometimes overlooked. But this idea of planned increments versus rapid iterations. So, and the idea being the difference between waterfall and planned increments is that you need to start out with a very clear idea and a fully formed specification of what you're going to do. And we know in reality that's not the case, right? By the time, as you go, you need to learn as you go, and you need to find out what's important to the client, and you can adapt. So therefore, with Agile and with this rapid iteration, it starts with more of a range of things and uses that to understand what's important, and you move towards a better product, and it allows you to make course corrections along the way and incorporate learning. So another example of this is this example here. This one comes from a guy called Henrik Nyberg, one of the kind of like the chief guys that blogs about this kind of stuff. But he uses this example, and the idea of this is how do we learn how to deliver what works? And I'm talking about software, you're talking about better buildings. But the idea is not like this where you deliver each a set of parts where it's not until the very end you actually get the customer something that they're actually satisfied with and they know, because you've invested a lot of time to get to that point, and you might find that you get to that point and it's not what all customers want and not what everybody's satisfied with. Whereas instead, if you can establish a very early prototype that sort of represents what the main aspects of performance are, and you can learn what quality is, and what's important to people, you can iterate upon it. So for example, a skateboard might be perfectly happy for somebody who wants to skate in a skate park, and it's their idea of heaven, right? Whereas for somebody who wants to travel long distances with baggage and stuff, they need more. A skateboard's not going to cut it. So by having that early prototype, by having a simple version, a simple concept of things, you're able to use that as a conversation to really understand what quality is, and how to build a better product, or in this case, a better building. So with all that kind of agile sort of thinking in mind, I'm sure you can kind of draw the parallel to building design and so on, and moving throughout the design progress. We've used these methods over the last number of years to really learn from the market as to what works and what doesn't work, and we do that through a number of mechanisms. First is we release software. People use it, they provide us with feedback, and over the years we've had the original kind of building performance analysis features with Autodesk date back to Revit version 2008. You've also got things like Format, Greenbuild Studio. Earlier this year, we end-of-lifed Ecotect because we're replacing it essentially what you're going to see today. And then we also have technology previews. So these are like alphas and betas and ways for people to experiment with new things that aren't necessarily in production, but it's a really rapid way for us to learn what works for people, what resonates, how to build these things, how to solve that real problem. Do you need a skateboard or do you need a car? Or does a skateboard and a car work for different jobs at different stages in the process? So these are a list of projects that you'll have seen us talk about over the years. I mean, this time last year we were talking about things like the energy cost range and so on, energy plus cloud. And this year we've got things like Project Salon and Project Aquila. Salon is still going. Project Aquila is a new project. And at the same time, obviously, we work very closely with customers, through just direct meetings, like at these shows, site visits, our user forums, every means possible. We get that information to understand as an industry, what is it you need to make these tools better? So there are feedback and learning mechanisms. So over the last, count back as many years as you want, back to Revit 2008, we've been doing all this learning, constantly refining, and we're at a point now where we've really sort of brought things together in a much more cohesive way. And we can now sort of present to you sort of what we believe is really needed in the industry. And this is at a very, very high level. But for one, this much is sort of obvious, but at the building energy environmental performance level, you're dealing with a complex system, and you need to essentially get to a level of whole system optimization. Now, I use the word optimization a little loosely because it's a complex system, it can never be fully optimized, but throughout the design process, there's a lot of opportunity to do better that's currently overlooked and missed. So there's definitely opportunity there. And in the domain of particularly energy analysis, a lot of the tools have focused in particular on solving that part of the problem in a great degree of detail. And that's fine. We have an abundance of tools that do that, but it's actually only one critical part of the overall problem that's needing to be solved. And there are two other parts in this construct that I'm using here. The other is stakeholder engagement. And I've really just sort of coarsely classified this as owner, architect, and engineer. And the reality is that those existing tools today have very much been heavily weighted towards engineering use. And architects and owners, to a further and further extent, have sort of been left out of the loop, and it's just too complex for them to get their heads around and so on. Whereas really, designing and operating a high-performing building is a team sport. It requires a team to come together and take joint responsibility and accountability over decisions that are made and assumptions that are made in the models that you make and so on. And it needs to be much more transparent than it currently is, and it shouldn't be as complex. The other thing as well is that it needs to traverse the entire life cycle and the different processes that we go through. So from the very early stages in the design process, all the way through to schematic design, detail design, into construction and operation, we need a clear and consistent way to be able to get a quick handle on these things. So the simple way to put this, it's very easy to say, but it's kind of hard to do in practice, is that we need to get all the right people with all the right information at all the right times. And again, I would just use the analogy of skateboards and cars, different levels for different parts. So we're not trying to, solve this entire thing or say that this is the answer to every energy analysis question that you're ever going to need, but it is providing a certain level of functionality that traverses those main things. So if the basis of a skateboard is wheels and a board and an axle and so on, these three main pillars are the same aspects of the system that's needed. So what we're going to introduce to you today is really the culmination of a lot of that learning and work that we've done over many years, and we've called it Insight 360. And it's a new cloud-based service that we're launching actually here at the show today. And if you've been using any of our tools for some time now, you'll see a lot of the things that you've come to learn, but what we've done is we put it together in a much more cohesive way. It's now out of things like beta and labs and so on. It's now a formal product, and it's kind of showing Autodesk's commitment to ongoing investment in this area. And we really believe we're at a point where we have a lot of value and functionality that people can use, and it's particularly suited to architects at that conceptual and schematic stage. It can do more than that, but you'll see as I go. But the way to kind of understand how I like to position this is if you imagine a continuum of knowledge and skill of building an environmental, energy and environmental performance from sort of novice to expert, and the building life cycle from concept to detail, or put differently, for an existing building, from a sort of preliminary assessment to a very detailed assessment. If you imagine that as a continuum, the way Insight 360 sits is that it traverses the entire amount, and at the very highest level, it provides this very fast, outcome-driven way, and I'll explain what I mean by that in a minute, to a guide to energy environmental performance. So it's not about analysis or simulation or modeling or anything. It's about putting the information first and helping people make better decisions and showing them the impact of their decisions in a very, very clear and easy way. Next to that, critically, key architectural design decisions that are made at that sort of conceptual and schematic stage around things like massing, orientation, window-to-wall ratio, shading, materials, all those key architectural decisions that have a major downstream implication to the overall efficiency of the building. At the same time, we're not intending this to replace the existing tools and workflows. Like, you'll still need to do lead energy modeling, there's still measurement verification, there's still detailed HVAC systems analysis. There are a lot of tools that already do that, and we can support that in a number of ways. First of all, through interoperability with things like GBXML, DO2, and Energy Plus Export, but then also by being able to frame the nature of that information in such a way that helps a broader audience of people understand the level of detail that goes into a lead energy model and so on, and understands, for example, that a lead energy model is one diagnostic point of performance of a certain energy cost, but the owner's actual energy cost will vary based on how you do these things. So it helps understand those kinds of things. So I'm going to give you a quick overview as to what it is before I sort of dive in and show you the software. So I won't spend too much longer in PowerPoint. I know you came here to see some software. But what we've put at the center of this thing is a thing we call the energy cost range. And we've given, for a very long time, people have asked for, give me this clear indicator of performance and how I'm doing. If I do an analysis and I see 1, 2, 3, 4, 5 kilowatt hours, well, is that good or is that bad? So what we've provided is a simple dial that shows not only a single value, but also a range of values, which is based on your current level of understanding. And it moves from red to orange to green as you go from not achieving code, which is actually 90.1, 2010, to somewhere between code and the architecture 2030 benchmark, and then once you're past 2030, you're green. And it's that simple. And you'll see that as we go through the examples. But this indicator gives you an idea of how you're doing, and also a value of energy cost. And we use energy cost because everybody understands cost, running cost. You ask people what EUI is, and 50% will go, I don't know. And they don't have an inherent sense, and it doesn't necessarily speak to the owner value that energy saving could actually have. So the performance indicator is one part, but of course the key to that are the parts that influence that performance. So in one respect, we've got obviously the location, we've got the building geometry itself, which can vary, again, from conceptual to detail level. And then we've got this concept of factors. And factors is just a simple word for the things that influence building energy use. And we've broken them down into a series of parts, which we describe them as, I describe them as MICI, if you've heard that term, mutually exclusive, collectively exhaustive. It more or less captures the entire landscape of possibilities. And it takes each value, like take, for example, roof insulation, and it does everything from minimum roof insulation to maximum roof insulation, and then computes all the possible combinatorics of everything in between. Okay? And we do some very clever things how to do that without spending years and many, many more kilowatt hours of energy on the actual compute time. So we've got some very innovative methods using the cloud to do that, and that's what I'm going to show you with. And it gives you a very nice interactive, rapid feedback on the impact of things. So for example, we can see, for example, if you start to adjust ranges, you can see how performance changes from red to orange, energy cost saves. We can show you visualization of heating and cooling loads, which are calculated using Energy Plus. And then, of course, we can do very quick scenario comparison to kind of show the path to things like Architecture 2030 and so on. So we've really put comparison and that rapid feedback really at the center of this overall experience. It's also cloud-based, so when you run these things, it's all accessible from a web browser. So anyone who has a web browser can access this. And it really allows you to build sort of like collections of analysis and use this tool to really tell whatever design story you're trying to tell to an owner or to a design team. And finally, of course, notice I've put this last sort of on purpose, because traditionally we've always kind of started with Format and Revit and you do your analysis. But in fact, Format and Revit is just one of the ways to feed this. You know, that's about geometry, and it can be about other things as well. Really what we're doing is we're putting the actual energy and environmental information first in a place that's really easy to access, very visual and interactive so that you can see it. But of course, Revit and Format provides the geometry and the analytical geometry, and I'm going to show you a lot of that as well and the improvements that we've made in that area. So the basic workflow, and this is the last slide before I get into demo, I just want to give you an overall. So to use this and to create models, you do actually need Format or Revit, but once they're generated, you can view them in the cloud. You don't need that anymore. But all you need to do this is a subscription to either Format 360 or Revit. So just out of curiosity, how many people actually have access to Revit in their offices? Okay, so again, actually, like 80% of people have Revit. So if you have Revit, 95% chance you have subscription, meaning you have access to this. There's no additional cost. And there's no cloud credits or anything. There is for one part of it, the daylighting simulation at a certain level, but for the energy analysis, it's all you can eat. Basically, all you have to do is, it is as simple as this. To get started is just set your location. There's no additional information required, because actually, as I explained, we compute everything, every other possibility, and that's how we give an outcome-orientated feedback on things. And what we do is there's a simple button that just says Generate Insight. So again, we're trying to get away from terms like analysis and simulation and so on, just to say, well, what is this about? It's about giving me some answers. And what that does is it automatically creates what we call an energy analytical model. We use that term just to differentiate it from everything else that the energy model is. That's really the geometry, okay? And then also, this is when we run these millions of combinatoric simulations. And as I explained, we don't actually run millions of them. We don't have to. That would be inefficient. We've got some very clever methods for running an array of simulations and combining the results that has a small loss in accuracy, but it's still well within the margin of error, still well within sort of plus or minus 10%. But it gives you this very, very full set of parameters and factors that drive overall performance and help you understand the immediate cause and effect feedback on things. So you open up Insight, you explore the energy cost range, factors and savings of things, and you can do things like visualize heating and cooling, do solar and lighting analysis, and then of course, lather, rinse, repeat, go back, continue to enhance your model and so on. So that's basically the overview of everything, and so what I'm going to do now is get into a demonstration, all right? Okay. So I'm just going to start off with this view in Revit here, and again, this is a simple example trying to represent an entire building life cycle. In reality, there would be thousands or hundreds of points along the way to this, many iterations. It's not a linear process, we know that. I'm just trying to help you understand how this thing can actually span this process. Of course, you don't have to start in Revit, because a lot of conceptual design doesn't actually start in Revit. You've also got Format now today, which is a very nice conceptual modeler. It's available, again, in a browser, also on iPad and Android and so on, but it's got this nice, push-pull feel to modeling. You can do a lot, but the point here is that from the very earliest stages, from the moment you have the most basic representation of the building on the site, You can represent it with a mass or as many masses as you want. You can add mass floors and so on. You can run an analysis. All you need to do is set the location and then click Generate Insight. Similarly in Revit, all you need to do is from any one of these models here, similarly from the Insight plugin, which for Revit, in the meantime, you will need to download. It's a separate plugin. Just click Generate Insight, and that'll automate the entire process. And that's the only part of the process that takes some time, and depending on the size of the model and the complexity of the model, it can take anything from a minute or two to return the results to you, to maybe 10 or 15 minutes is what we find on average. But the wealth of information that you get back is enormous. And the 1 to 2 minutes works great at those early stages, and when you get to those detailed stages, 15 minutes sounds like a lot, but it's really not when you consider what you're actually getting. So, I'm going to explain how this happens later on a little bit of the actual analytical model creation, as these are sort of key features of Format and Revit, but I want to for now focus on the Insight 360 user experience. So when we run the analysis, I can launch it from within Format or Revit, but also you'll see it's in a browser, and this is sort of like the Insight 360, your home page. Kind of consider it like a gallery of all the analysis that you've done and so on. And I can organize these any way I want. And in the example that I've got here, I'm just starting with this basic U-shaped mass, and I'm going to go into it here. By default, they'll go into this uncategorized group, and then from there you can organize them into groups, and you can use those groupings whatever way you wish. What this provides at a very high level is a collection of all your kind of models, and I'm going to come back to that later. But I'm going to show you the basic elements, and again, anyone familiar with the energy cost range is going to understand a little bit about this and see what we've done with this. So the first thing that we see is we've got this model view. It shows us our location, where our location has been sent or set. We've got this overall energy cost range, which I'm going to get into a little bit more. A lot of people ask, do you also have EUI? And again, you just flip over to EUI if you want that. The EUI only works on the little dial. It doesn't work on the individual factors. But that's, again, another little thing that we're constantly incrementing towards. But we are trying to encourage people to look at cost. People have generally avoided it because they're nervous that owners get too much of a sensitivity to it and so on. But you'll see with the way we're approaching this, it's a lot safer to talk about cost now, which is a good thing. This model that you're seeing is actually the GBXML that's been created through the Format and Revit translation. And as part of that, if you remember, all I did was draw a blob of geometry. And what this has actually done is in the background in the cloud, it's actually created the thermal zoning. So if I sort of expand the model, you'll see what actually constitutes that analytical model. So you'll see the ASHRAE 90.1, perimeter core zoning, to make sure that that simulation is done right. So even though the building doesn't have any interior layout yet, we still treat it like it does so that we get an effective simulation. There's all kinds of cool things you can do with that viewer. But basically, the main interaction here, if you haven't seen this before, is that this is the energy cost range. This is our overall benchmarks. Here we can see our current mean energy cost is 18.8. That's dollars per meter squared per year. ASHRAE 90.1 will be 16.8, and Architecture 2030 is $7.30. Now that's derived from the EUI that is Architecture 2030, but we're keeping it all a consistent scale. And what you'll see here is these are all of the factors that we have. Okay, so I'm just going to I'll sort of zoom out so you can sort of see them all. There's quite a lot there, but there's everything from lighting to equipment, envelope, glazing, operating schedule, HVAC, building orientation, window to wall ratio, PV, all the big buckets that really sort of drive the overall energy balance in the building. So this is what I meant by the whole landscape of things that we do. And remember, everything that's in here is all computed together. And when you do that, it completely changes the nature of your interaction with energy analysis results. So you're no longer looking at points of performance, and you're no longer overwhelmed with lots and lots of input. It's great, you're turning it on its head and saying, right, if I compute sort of everything to a certain level of detail, and then understand what that range is, I can then use that range to understand the value of things. So the example that I'm going to do here is actually orientation. I like this one because it's always asked on a project, and it's usually requires somebody to build a model, run 8 other models, and then see what the impact is. We've just, in one button, we just automatically computed all of those. And I'm going to use this as well just so you get some idea of the interaction model with the energy cost range. So you can see it in a little bit more detail now. You'll see there's the mean, there's the max, and there's the minimum, and there's the Architecture 2030 goal. You see we're red, and we're not very happy about it, right? And in orientation, these are all the range of orientations that we've run. And what I can do here now is, at the moment, this mean is being calculated the fact that, well, you haven't selected anything yet. we don't know, so we're somewhere in the middle, okay? That's what it's been calculated off. So if I wanted to see the sensitivity of this building to orientation, and this isn't a particularly exciting building. If you look at it, I'm an engineer, so I have no imagination when it comes to modeling something. But what you'll see is that if I sort of scroll this from the very left to right-hand side, you'll see it goes from 18.4 to 18.9. So it's 50 cents a square meter, or around 5 cents a square foot of energy savings through orientation. Now, you'd say, okay, well, I've heard that kind of thing before based on a single simulation. Surely it depends on all these other things, and what you'll find is it doesn't. Within around plus or minus 10%, whatever we set any other parameter to from now on, that what did I say, 5 cents or 50 cents a square meter remains around the same. So we're able to isolate the value of individual measures. So what I can see here, for example, is the best orientation happens to actually be the current default orientation, 0. If I was to, the next best is to completely flip the building 180 degrees, I get the same, but everything else is kind of a little bit worse. Now, the interesting thing about orientation is I've never actually heard anyone orientate a building just to save 5 cents a square foot, or it's not going to happen. And the other interesting thing is orientation is just another expression of building form. And so what we're really more interested in is the shape of the building itself. And that's really when we can get into more of the modeling, different forms, and generating. Is that me? No, I think so. But we can get into that. But again, it answers the question very, very quickly. And there will be building forms where you'll see a much higher sensitivity to that. But in this case, it's not particularly. But it gives you an idea of the interaction. And as you'll see from that, you'll see the range reduces slightly because we're now reducing the problem space that it's calculating. So that's orientation. The next interesting one that I think is very interesting at early design stages as well is window to wall ratio. And for each main elevation, north, south, east, west, I'm just going to flip these over. We've computed everything from sort of 0 to 95% with everything in the middle, okay? And so say, for example, what we can see here, just by looking at this visually, the south walls, as you would expect, are pretty dominant. And if I open that up, I can see, what if we went from, now at the moment with this, going from sort of, 0 to 95, the mean is sort of sitting in the middle, which is somewhere around code, a little bit higher than code, 40%. But if we wanted to see the sort of full extremes, I can't even bring myself to make a building 95%, so I'm going to sort of put it to 80 to 90, that kind of range. If I was to do that, all the way down to that, 90 days. So you see $2.80 a square meter for that glazing elevation. So again, everybody likes views. If you want a view, if you want more glazing, you want daylight, it's really important. I certainly wouldn't like to be in a building with 15% glazing or whatever in it. You can get to see and understand the cost. And so what you can do is you can say, well, look, maybe I haven't decided that yet, but I know I'm going to be in the sort of the 30 to 80% range, right? So we're leaving ourselves open there. Maybe I have a building where I know there's 0 glass on that, then I can set that. I'm starting to incorporate some of my known knowledge now. But what that allows us to do is that as we go through, if I just do this a little bit more for each one, because I'm going to give you an example of how you can actually use this now to start again telling stories, making decisions around window to wall ratio and other things as you go. Here we go. So now you'll see that what we've got. What I'm going to do now is I'm going to do what we call create a scenario. So if I do this, what it's like doing is basically bookmarking that set of states of the factors, right? So I'm going to call this 0 orientation and 30 to 80 window to wall ratio, okay? So now, from what we can do from here is we can say, well, this still isn't really telling us a whole lot. We can understand the sensitivity of things, but the first question you really need to talk about as a design team is, what is your performance target and how are you going to get there? What are the kinds of things you're going to need to do? And that will help reduce the problem space. Remember, this set of factors really represents everything from potentially a very old existing building to a much more higher performing new building. So we've got a lot of opportunity to very quickly reduce this problem space and not only get the performance, the energy cost down and understand the impact that each part makes along the way, but also reduce the range. And in other words, increase the certainty of the overall result. So for example, one I always like to start with is, well, operating hours. People sort of forget about that. When you do a lot of work doing energy analysis, make a lot of assumptions about hours of operation, set points, things like that. and when you get this question of, well, how accurate will this energy analysis be? Well, it depends on how you operate the building. As long as you operate it reasonably, you maintain it, you invest in commissioning, you invest in maintenance, all these kinds of things, it will operate with other things along the way. So you can very simply see here, the operating schedule has a huge impact. And again, the full range of kind of 12.5 to 24/7, 22 to sort of $16. It's massive, right? But for most buildings like this, you're talking about that kind of range. That's as specific as you really need to be. And again, it still leaves you a little bit of padding in that range so that you're not presenting the client with one particular number that by definition is probably wrong. Next, you can do things like, let's say, lighting efficiency. And I'm just going to do a couple of these just to sort of show you. So again, a very wide range, sort of current high performance would be sort of like in that kind of range here. I can, if I want, be very specific and sort of set it to something like 0.3 or 0.7. But again, we're not worried about the specifics yet of how we do this. This is a targeting exercise. And as we go through the process and start to actually design our building and pick our systems and see what the actual lighting power density is that we can document in things like the Revit model, we can come back and refine these things and track it throughout the process. I'm just going to do one more change here. Say, for example, if I do that, and then what I can do is I can bookmark that example as well, right? I'm just going to call this. I just want to get you some idea of the workflow and how it sort of works. And so now with that, what I can do is I can see the comparison of those two states side by side very quickly, and it'll automatically sort them from left to right. One of the other things that this does, which is really nice as well, is that we're using DOE 2.2 for our whole building energy simulations, those millions of simulations we're running, because it's super fast and it is a pretty good whole building, particularly at that level. We're not doing very unusual or complex HVAC systems. We are doing a full range of efficiencies. But one of the things we're also now doing is using Energy Plus to do some dynamic heating and cooling load calculations, which is a first step towards using that to do more energy simulations. And one of the things we can do is to present those results directly in context in the model. So for every model that gets sort of run, you see this, for example, is heating load, and you can see the areas of greatest heating are the darkest blue. So you can see these ends of the building here. The cores are pretty safe. So you can see where you've got some sort of greater load intensity. And this is a conceptual model. You're at an early stage. You've got overall building types. So what you're really seeing is differences in orientation and envelope. This is cooling load. You can see there's a few spaces there that are subject to a little bit more heat gain, particularly these sort of areas here. So starting to give you clues to what this is. And also it's helping to explain to a client sort of what an energy simulation is. Heating and cooling loads, of course, are different. But they are a part of that overall equation, and that carries through the process. And as you get later into the process, into specifying, what a particular room is and what its, occupancy and lighting is, for sizing terms, you can start to use this. And just for the engineers in the room, to caveat, this is just the room and space side load calculations. We're not doing system side coil sizing just yet, but this is just using Energy Plus for that more detailed dynamic calculation. So what I'm going to do now is, if you remember, so that gives you an idea of the overall kind of interaction model around the energy cost range, the factors, the benchmarks, and sort of how you do these things. If I go back to my example here that I've sort of illustrated in Revit, what I've got here is that original U-shaped model, and then I'm going to do some sort of mass form exploration. So again, you could do hundreds of these at an early design stage, particularly if you start to plug in things like Dynamo, start to do generative geometry, and then into sort of more schematic stage where the Revit, interestingly, the Revit model gets interesting because you start to articulate details like curtain walling and shading and interior room layout, which starts to change the thermal characteristics of the building a little bit, all the way through to sort of a detailed design where you've got particular room placements, and even to the point where even you'll have specification of, again, numbers of people, lighting power density at the room by room level, all the way through to operation, where I'll show you this example. So what I've got here in Insight is an example that I can go back to. This one here. This is my sort of my whole story. And again, this could be many, many more stops along the way, collected in a number of different, but I'm just trying to present it in one go here. So this was this was the model that we just did. And what I did here was I created a series of steps that shows essentially the path to Architecture 2030. So starting, with that case that I had of 30 to 80 window to wall ratio, haven't decided that yet. Pushing our lighting equipment and schedule, pushing the envelope, HVAC, and then finally PV is what really we're required to add. And you'll see we have some factors down the bottom to do with photovoltaic, which again are very high level and conceptual. We have some tools that take this to the next level. I'll point you to a class tomorrow that will take this workflow into more detail. But for example, here we can see very quickly, well, what percentage roof coverage would we need to achieve these kinds of things? So again, very high level targeting and feasibility. I can go from sort of 60 to 70 or do somewhere in between, and I'll get the immediate cause and effect on what that is. But basically, this just allows us to sort of ballpark, agree as a team, get a shared understanding of what our overall strategy for achieving the Architecture 2030 goal would be. To take that to the next level and say, right, again, everybody likes windows, so we want more windows. How are we going to fit them in? What's going to be the cost of windows? And I use this example here to do a window-to-wall ratio study, where this one in the middle is our original conceptual target that we sort of had agreed on. And if we pushed all the windows up to 80, 80, 80, which all I needed to do was just move those dials, save it, put it there, well, you can see it blows our chances, right? Windows are expensive. We love them, but they're not very energy efficient, right? They can be, though. Window-to-wall ratio 65, 65, 65. Again, it's better. It's somewhere in the middle, like you would sort of expect, but you can see it's still going to blow that. If we went 50, 50, 50, we can achieve it with that. But if we want to push the windows, then that's when we can add a higher performing glazing. So we can very quickly match those things, and you'll see that each one of these scenarios, if I was to go to the one that I picked, 65, you'll see what I mean. You'll see the actual factor states for each one. So you'll see, for example, that we're picking a higher performing glazing in the higher performing range. And again, we haven't computed every glazing on the planet. That's not the point. We've got a suitable range, and at a later stage, we can start to get to the specifics of how we do that. Particularly when you see that the choice between these two is like, small amount of difference in the overall scheme of things. But you can see here that the higher performing glazing, along with 65 and other elevations, and on the south, we reduced it a little bit to between 65 and 50. We can still stay in that goal. So again, without having to do lots and lots of modeling and so on, I could do this at a very high level, very quick, and feed that back. And that's what gives me enough of a basis now to start to do a sort of a mass form exploration. So for example, if we had some freedom on the site and we said, well, maybe we started with just a blob and we started to explore U-shapes, T-shapes, L-shapes, stepped facades, whatever, you'd actually see at this very high level that if we went for something like a stepped facade, this is with the exact same factors, very quickly set up, you see the cost of that is more like 9. This has been rounded up. Again, trying to help people get a little bit away from the dot numbers. If you click into that, you'll see exactly what it is. Higher performance, so higher cost and higher range. So again, if somebody really had their heart set on that design for some reason, they could do it at least knowing that it is having an energy cost. Again, energy isn't the only thing that drives building form. Similarly, we can see that an L-shaped building is at least as efficient as what we've got. Courtyard is a little less. And so we can go through as many of them as we want. In other words, the way I put it, and I'll show you this in a minute, as fast as you can model in Format and Revit, is as fast as you can fill this thing up and do your comparisons. It really is that easy in the middle. And I'll show you some of the magic on Revit there that we're also very excited about. And so later on, you'll see then we get into a more schematic model. So I'll show you this one in more detail. And you'll see that the model itself, we're now moving from this sort of mass form, automatically zoned model because we had no spaces to a model that now has spaces in it insofar as that. I don't mean spaces in the Revit model, but what I mean is we're now starting to designate space usage inside the building. Say, I think this is a school, so we're saying these are classrooms and these kinds of things. But see, the model itself is a good deal more complex. The internet connection here is very slow, so that's why it's taking a little bit of time to render. But what you can see here is with the exact same factor setting, that due to this particular building geometry that I've derived from Revit, we're still staying on target. In fact, we're doing a little bit better. So we could do one or two things. We could maybe go back to a slightly lower performing glass, save some money, or continue to push that envelope. But the point I wanted to make here is that all you need to do is bring your Revit and Format geometry. You get this full range of scenarios, and you can very quickly see what it is. And again, there's two ways you can use that. At an overall targeting level, for getting a sense of what the value of those factors are. But I think critically for architects, making decisions about the shape of the building and the layout of the building and where you put glazing and where you put shading. They are big deals that have typically been looked at in parts, but never really in a holistic way, as a whole. So this would be a good time now for me to show you what's actually going on in the Revit model. So again, here are our models. And what I showed you here, in this model here, I showed you this in the model viewer. This is the energy analytical model, as we call it. So this is essentially the GBXML that you're seeing now in Revit that gets automatically created. You'll see, if you look at it in plan, you'll see the perimeter core zone. You see those little sketchy lines in the corners? That's just a byproduct of the computational method that we use for calculating this. Over time, we're reducing them. The only downside they have is that they take slightly longer to compute, but they're very accurate. And they look a little ugly, but it's very, very accurate. And in fact, it's a lot more accurate than a manually created energy model. But that's it at the conceptual level. You can't see that in Format. That happens in the background, but you can see it in Revit. It gets more interesting when we look at a model like this, where you start to now see more details. So it's now translating on a curtain panel by curtain panel basis where things are. So for example, if I was to go to this view here, surfaces, I get to see the surfaces on their own. And if I, for example, wanted to check all of the, let's say, well, where's all my slab on grade, or all the surfaces that are in contact with the ground, I can create a view that just shows that. I can say, well, show me all my interior floors. And the cool thing about this is that it's deriving it from the detailed, rich Revit model geometry. So there's no simplification of things, and floor areas and volumes are all a lot more accurate than a normal manual takeoff of an energy model, which is fine because it's used for comparative purposes, but it requires somebody who knows what they're doing to build that model, whereas this is completely automated. And this goes all the way up now to when you get to a detailed model, or what we would call a detailed model with full rich building elements, ceilings and curtain panels, all that good stuff. If we open up that model here, you can see it's a lot more detailed, right? And again, some of the really nice things you'll see, it automatically identifies where there are ceiling voids and things like that, and treats them as ceiling voids. So you don't have to mess with any of that stuff. It just, whatever you've modeled in your model. The only requirements this needs, because again, a lot of people have tried the old sort of GBXML export, and they've realized that you need to rebuild the model and so on. We completely rebuilt this feature because we know that people will not do that, right? Some engineers will because they need to build a model, and that's totally fine. But anyone else, has just not enough time in the process to do that. So the only thing that this feature actually needs is that the building be what we call reasonably enclosed. And what that means is that if, for example, you didn't have a roof on the building, well then we can't compute that there are spaces beneath that roof, right? What you would get is a bunch of what we call shade surfaces. And small gaps and overlaps, like when architects model in Revit, they don't do it particularly precise. There's all kinds of little things that are perfectly fine for architectural modeling, but can cause other translation issues a big problem. So the point is, if you can do basic architectural modeling in Revit, from conceptual massing through to building elements or any mix in between, you can create this analytical model, have automatic zoning looked after for you, and this kind of model produced. And I said the one big difference between it and a manual model is that, if any, it's just a lot more detailed, a lot more complex. I mean, these can be 100 megabyte GBXML files, which we're constantly working on getting smaller, which we can, but it's just at the moment, the main thing is it accurate? Does it do a good takeoff of the building? And again, of course, you can export that GBXML and use it in other tools. So yeah, and I just show you some of these things that are to show what it does. It automatically, for example, identifies where there are things like shades. Not everything in a building is a purposeful shade. Some is sort of incidental, like for example overhangs. So wherever in the building that you want to see, let me just turn the architecture back on so that you can see it a little bit more clearly. There we go. You can see where we've actually identified exterior shades in the building, right down to even things like columns and so on. It's very, very detailed. So the energy model is directly, the detail of it and the size and complexity of it is directly proportional to your Revit model complexity. So if you move from concept to detail, it works seamlessly. And all this stuff that you're seeing here is new as of Revit 2016. So if you're not upgraded to that yet, you'll want to get this to use it. And Insight 360, we recommend you use 2016 or 2, which is the subscription release, which has some enhancements to it and so on. So that's that side of things. So the one thing I wanted to sort of finish on in the demo was to also just explain how, Agile energy analysis for architects, but also remember that thing about the overall building life cycle. This interaction model can also be used to represent an existing building. And in an existing building, when you do an analysis of it, there's often a lot of things you don't know really. What are the properties of the walls? What's the property of the glazing? What are the hours of operation? So again, you've got a lot of uncertainty in these things. And so what I did here is I just used that same analytical model, but I built a bunch of scenarios to kind of represent very quickly, again, just consider the amount of time it takes to do these differential studies, to represent roughly what an existing building hypothetically might look like. And you'll see here, first of all, very high energy cost range. And if I open up each of the factors, you'll see what each one actually contains. So again, this is a very, very detailed model. Remember, even though this is an existing building, I could use a very quick conceptual model with automatic zoning if I wanted to do that. Guys tomorrow will be talking about what we call rapid energy modeling for that kind of thing. I'll give you the details on those classes later. But basically, what we can see, for example, with lighting efficiency, you'll see, for example, we're in the high range, plug loads, infiltration, the building is leaky, and again, you get to understand the sensitivity of these things. And again, very quickly, I said, just built a few scenarios to help sort of, again, plot some kind of path to this. And again, what's interesting about this, you can very quickly combine different combinations to see, what your different options might be and what order you might want to do things in and so on. The point is building the scenarios, you don't need to be messing around with Excel, you don't need to be running lots of simulations sequentially and then realizing you got one thing wrong and go back and change them all again. It's all sort of done for you and very, 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 very fast. So, let me just check if I got that. Yeah, so that's that. Let me just finish up with a few slides here. I'll leave some time for questions. So, going back to my original thing of Waterfall versus Agile 2 sort of spectrum, neither is really wrong, but some are more suited to different jobs than others and different sort of processes, and this is sort of helps sort of position sort of like where the industry has been and somewhat stuck around the area of energy and environmental analysis, and these things being highly skilled, time-consuming, very input data-driven, sort of single simulation at a time, and you might do 10 or 100 or 1,000 simulations even, but they still require, it's still very difficult to manage that uncertainty aspect and communicating to the client what those assumptions are. They're largely tailored towards detailed design and sort of operational energy use, which is great, but it makes them hard to apply early on. A lot of them use BIM, import and export, but they have very special modeling requirements. You must build a model this way, which again, our learning has shown that some people will do that, but for the most part, most people just want to model. They've got a lot of other reasons why they're building that model that way and just have that generated analytically. A lot of the methods and tools are also very regionally specific. So again, lead energy modeling is one particular flavor of analysis. Of course, as well, I got to mention this, but they range anything from free to sort of buy, so to speak, up to expensive and also to use as well. On the other side, the way we're positioning Insight is that it's a lot faster, it's easy for anyone to access. It's it's reasonably comprehensible handle on overall building energy use and costs and managing expectations. Uniquely, it's outcome driven, and we've got this concept of ranges and helping change the mindset around your approach to analysis. And again, thinking of that iterative process of learning and incorporating learning as you go. We're trying to provide something that can span the whole building life cycle, at different levels of detail. Again, we're not saying that this is a replacement to things like lead energy modeling or very detailed systems analysis, which has got a distinct purpose for answering those specific questions. It's fully BIM integrated with no real special modeling needs. Although we do point to things like Architecture 2030 and so on, because we run pretty much this full landscape, it's pretty globally applicable, right? Buildings all over the world are influenced by the same things: climate, their overall architecture, materials, how they're operated internally. We've captured that whole picture in a very simple way. And again, here you only need a Revit and Format subscription. How to get it? All you need is a Revit and Format subscription, if I haven't mentioned that already. For Revit, you will need to download a plugin, but it's an all-in-one plugin, and you'll see everything that it contains. I've actually only shown you a part of what Insight 360 actually contains, right? And I've done that on purpose because I wanted to leave a teaser for classes tomorrow with some of my colleagues. First of all, David Shear is giving a class on integrating solar power and design performance analysis tomorrow at this same time slot. So there are other aspects in Insight 360, which again, if you've used our tools before, you'll see But you'll see we've now got the lighting analysis and the solar analysis now integrated as part of Insight 360 and how those tools talk to the energy cost range and so on, and some of the more specific solar and lighting based workflows that you can get into, again, using your Format and Revit model. So I highly recommend if you can check that class out. But again, we're trying to provide a full range of analysis tools. And then Mo and David is going to give a class on rapid energy modeling, so using these tools and more of these tools and more of what's behind the scenes here in a variety of workflows for rapid energy modeling at an urban scale and for large building portfolios and so on. So you'll learn a lot more there. If you found this class useful, I recommend this. And then finally, for more information, you can check out our new blog. That's the new address for our blog. If you go to our old one, it'll bring you to the new one. And if anyone has more questions, you can come to see us afterwards. But I've managed to do this on time, 10 minutes left. I think that's a first. So yeah, any questions? Yes. Yeah, so I mean, like we've done a lot of, so yes, I'll repeat the question. So have we compared the results to any accurate energy modeling? So I'd sort of maybe want to, what you mean by that, but no. So yeah, so we have done extensive testing around, well, it's a long story, but yes, I mean, basically starting with things like ASHRAE 140, the basics of what you need. Remember, we're using DO2 and Energy Plus as our core engines, so they are actually part of the ASHRAE test set, ironically. But the overall other results in terms of testing against other existing buildings and things we've done around this Project Aquila that we've got for metering, we've done lots of internal testing. And also too, in fact, we've got a paper that we're presenting at Greenbuild around the things like lighting simulation, validation, and so on. But again, the engines have been around a very long time, like 30, 40 years. The maths hasn't really changed. And the computation has never been the problem, the information has been the problem, and managing that. So I would kind of argue that, these single simulations, we all know measurement and verification can kind of, with the right information, you can represent what the building actually does, shows the information is right, but it's managing that information, so yeah. Anybody else? So yeah. Right. So you okay, repeat the question again. Thank you. I'll keep forgetting that. The question was, in the beginning it seemed like you didn't need Format or Revit, but then in the end it did. So you don't need Format or Revit to actually interact with those results, but obviously I was creating those results from models that were generated from Format or Revit. So if I was an architect and I had Format or Revit and I generated 3 models, I could share that with somebody who only has a web browser and to see those results. So in other words, to do everything I was doing in the energy cost range and visualizing the results and creating the scenarios, I don't need Revit to do that. But to generate the models and to generate the design scenarios, that's what Revit is used for and Format is used for. Yeah, I know what you mean. Yeah. Okay, thanks, Jacob. So a couple of questions there. And thank you for the positive feedback. First one was about utility rates. Can you change them? No, not at this moment in time. It's statewide averages. The natural progression of things, because remember, we're not stopping here. We'll continue our agile development, and the natural progression of things is to add more factors. We don't want to overwhelm people, but there'll be different factors for different things and the ability to customize them and so on. That answer your first question? Second question was more of a philosophical one about, do we still think that, if I get this right, at the conceptual stage, is it still really practical to use things like EUI and cost at a conceptual stage? And I absolutely think, yes, it is, because the interesting thing about energy analysis is that even though you're at a conceptual stage, you are trying to use the notional potential performance of the building as your indicator. So you're trying to traverse this entire sphere of things that are going to happen, and that's why the sort of the levels of uncertainty or range, without getting into the specifics, because as soon as you get specific, then I think it becomes invalid. But as long as you stay within those ranges, and like for example, if you're trying to decide at a conceptual stage between, and I'll really exaggerate this, like an L-shaped building or a T-shaped building, all the other things that point to that overall energy cost range, as long as they're sort of equal and on a suitable range, then the indicator you're going to get is whether the L or T is better. So I absolutely think it is valid. I think the key word there is we can hit this if we do this. We'll do the L-shaped part, you do your systems part, engineers, right? I'm assuming, I don't know, I'm making an assumption, I can't remember who put their hands up. I just saw you guys nodding at some things. And then the owner needs to do their part around operation. And again, it's back to this thing about managing the risk, managing the understanding, and it's a team sport. And it's let's not focus too much on the inputs, but what is this telling us? What do we need to do? And managing what I call the collective actions, not just the strategic design things we do, but also the things we do as a team together over time. I think so, yeah. And I think, again, that's why we're putting cost as a central thing, because we want people to realize you can make value-based decisions on this, and we think that'll have more effect on people investing in energy efficiency and decisions around energy efficiency when they know that these things have an implication.
Basically the essence of great design.
Thank you, yeah, so yeah, exactly, yeah. That. Sure, yeah, so Project Aquila is basically a labs project that we have that takes real-time sensor information, energy meter sensor information, streams it to a cloud-based service, and uses it to do a couple of things. The first is to put context on where these sensors are. These sensors are self-powered, very, very low cost. You can fill a building with these things and meter everything very, very cheaply. But every building, particularly old buildings, you have difficulty tracking where they are. So it allows you to attach in 2D and 3D where those sensors are and what they relate to at a conceptual building information model or a very detailed building information model. So that you can then understand what you're actually seeing, because one of the challenges with sensor information, you get just a lot of stuff and you don't know where it's coming from. So when the installer is doing it, they can actually map these things. And then it also does a series of analytics and reportage around energy savings. And just a nice, again, very similar to Insight dashboard for streaming real-time energy usage and so on. And longer term, the idea is to sort of bring these two things together where you can stream, connect the whole things together and have sort of real-time measurement and verification and so on. Yeah, so Ani, I don't have the time right now, but I'm sure Ani is here, but he's going to be doing a talk on that later on. I'll find out for you. You definitely want to see it. Okay. Yeah, so the question was, international projects, how does the cost work? And yeah, at the moment it is statewide averages, so you'd need to take that into account. I mean, again, that is on what we call our backlog of things to do to be able to change that. It's fairly simple, but no, at this moment in time there's statewide averages, and that can span a big range of things. But no, at the moment it is, cost-wise, it is pretty much US-centric. With relative ease, you could do a conversion, but it sort of would take away a little bit of the interaction. But again, I think the thing is, even for the effort it takes to do these things, the minimal effort it takes to do these things, if you can at least engage the client to sort of let them understand that this is if they were paying for energy in these terms, US sort of terms, it would cost this. It's some way you could start to communicate with them. But if that's a major barrier to you using a tool like this, well, that would help accelerate us doing that, but it's something we've got to do. Exactly. Yeah, and we think we have a platform and an interaction model here that lends itself to that very well. Again, we're trying to get away from very, very detailed dialogues with the data and information, and really deal with it at a sort of a higher level and work from this high level down. So yeah, so essentially all that's missing there at the moment is a utility factor and the ability to vary whatever you want for gas and electric. And then the next level beyond that is getting into more detailed tariff analysis and so on, where it gets even more incremental. But at the moment, no, it's sort of one size fits all for everybody. And again, if that's it, just to loop back to our process, again, when we release a tool like this and we get feedback and we look at, what people are telling us, if 80% of people are telling us, hey, that thing missing is a real deal to me, that helps us accelerate us doing that feature work. So we love to hear that feedback. Yes. Okay, so the question there was, when you've got your Revit model, is there a way to calculate window-to-wall ratio? So at the moment, no, there is no simple push-button way to calculate window-to-wall ratio from the model. But what you will get, if we still have time to show you, is that from the analytical model itself, you've got a table of the analytical surfaces, and it creates a schedule of analytical surfaces of which you'll see exterior wall and wall. And so what we know some people have done is created some dynamo nodes to connect and do the calculation for them. It's a very neat little thing, and that's something we can add at a later stage, either in Revit or the analytical model. But the other thing that's also a place we can put it is in the factor range itself. Push it back there, because a lot of people say, I want to push this data from the factor range into the model, and that's sort of feeding the current paradigm of, I want these specific properties in the model. Now, from a geometry perspective, you want them, but for other properties, well, it's just a matter, are they documented somewhere? They don't necessarily have to be in the Revit model, because it's a lot more costly to maintain them in there. But at this moment in time, no, we can't calculate it directly, but the information is there for you to calculate it with a couple of steps. So I think we're a little over. So if we want to wrap it up at that, if you want to come see me after for more questions, or we'll be here, not quite all week, but we're here for the next couple of days. Come see us by for any more questions. Thank you very much.